Hello everyone, and welcome to this session on Exploratory Data Analysis or EDA by Intellipaat. EDA is primarily used to see what data can reveal beyond the formal modeling or hypothesis testing task and provides a better understanding of dataset variables and the relationship between them. In this session, you will learn all about the EDA and its components. So let's move on to the session. Before we begin, don't forget to subscribe and press the bell icon to get latest updates from Intellipaat. Hello everyone, welcome to Intellipaat's YouTube channel. In this session, we are going to learn about how we can perform exploratory data analysis or EDA on any data. Let's take a look at the agenda for this session. First of all, we are going to start with the basic introduction of EDA, and then we will discuss the importance of EDA. Moving further, we are going to learn about the steps that are involved in EDA, and finally, to sum up this session, we are going to discuss a hands-on on Metro Cities data. I hope the agenda is clear to you. So without any further ado, let's begin. So what exactly is EDA? EDA or Exploratory Data Analysis is an approach of exploring the data in a way where you are able to gather few insights from the data. These insights may include the pointers that best explain the distribution of the data points, peakness, and other necessary information like relationship between each of the variables in the data. You are able to identify the underlying patterns which you may not be able to identify just by looking at it. You are able to remove the redundancies like null values and outliers. The idea is to use the processes and tools available to us to make sure that no stone is unturned when it comes to exploring the data. The main objective of the EDA is to understand which kind of solution, or if we are using the machine learning approach, we are going to use to solve the problem. This practice gives us enough room to decide the outcomes based on findings while doing the EDA. Now that we have a vague idea about what exactly is exploratory data analysis, let's go ahead and look at why it is so important for any aspiring data scientist to be thorough with the concept of EDA. So when we discuss the importance of exploratory data analysis, we have to cover some points. First of all, EDA helps us uncover underlying patterns and trends in the data that are not visible by just looking at the data. So let's say if you're looking at any data which is related to insurance companies, you might not be able to find the patterns in how the people are paying their premium just by looking at it. And when it comes to EDA, it will help you identify those patterns and actually work on those insights. Next up, EDA can highlight useful relationships between the data points to gather insights. Now, taking the example of insurance data again, we can actually find out how and why people are paying their premiums on time, or what are the different parameters which are holding them from paying their premiums on time, etc. EDA also helps in restructuring the data according to the problem statement. Let's say we have to create a prediction model against some data that we have. We have to know how we are going to structure that data. Do we need the outliers? Do we need the null values? Or do we actually need to standardize the data for further computations? So that is where EDA comes into the picture. And last but not the least, EDA helps in removing the redundancies from the data, which I have already mentioned, the outliers and the data imputation techniques that we are going to use to replace or either remove the null values. Now that we have a clear idea of what exactly EDA is and how it is very important for us to learn about the exploratory data analysis, let's go ahead and check out the steps involved in the exploratory data analysis. So the steps involved in the EDA starts from how you load the data into your program. That is where your actual EDA begins, and that is the first step of the entire cycle also. Once you're done with loading the data, comes the data visualization, where you use the data visualization tools. For example, if you're using Python, we have matplotlib, we have Seaborn, we can use Plotly to derive different plots from the data, which is going to explain the distribution, the peakness, and other important points like outliers, etc. Then we can also find out the relationship between different variables using data visualization. Next up, the third step is data imputation, where we are going to figure out how we are going to replace the null values or how we are going to deal with them basically. So let's say if we have a distribution which is a normal distribution, we can just simply replace the values with mean. If we don't have a normal distribution, let's say if it is positively skewed, the distribution, then we can replace the values with the median, or otherwise if the presence of null values is very minimum, or let's say less than 5% of the entire data, we can just remove those values or drop those columns. Now moving on to the next step, that is the outlier analysis. With EDA, we are able to do the outlier analysis also. We can identify which features has the outliers, and we can also analyze and basically remove those outliers. And if we want to keep them, we can take a decision on that as well. So that is also covered in the EDA on repeat. So that is also covered in the EDA. And last but not least, the fifth step is gathering the insights. So from all these steps that we have performed, we have to come to a conclusion that our data has several insights. For example, let's say if I am analyzing the IPL data like we have done in one of the previous sessions, what we have done is basically carrying out an entire EDA on that particular data, and we have found out the 10 best players of that. Repeat. We have found out the 10 best players from that entire data. So similarly, we have to gather insights from the data, and now that we have actually understood the steps involved, we have understood the importance and the basic definition of EDA, let's move on to the hands-on part where we are going to perform the EDA on metro data using Python. Before that, let's just quickly take a look at the problem statement. So we have the metro cities data, and we already know that subway system or the metro trains that we have in the various countries has been there for civilizations and has been helping the modern civilization to commute in everyday life. And it is a very big network all around the world. So we have gathered that data, and our job is to identify the underlying patterns by performing EDA, where we are going to use Python on the metro data. And in the end, we are going to gather a few insights from the data. So let's also take a look at the data set, how we have all these features: city, country, name, year last expansion, stations, length, kilometer, annual ridership, mil, and region. So we have also described the columns here. So city is basically the name of the city, then we have the name of the country, the name of the metro, the year it was built, and the year when the last expansion happened for that particular metro, and then we have the number of stations, the length of the entire network in kilometers, and then we have the annual riders, which is in millions, and last but not least, we have the column with region, which is basically nothing but the region where it is located in. It could be North America, it can be Europe, it can be Asia, or it could be Australia, and then we have Latin America as well. So we'll quickly go to the notebook and perform EDA. So let's get started, guys. All right. So this is our notebook that we have created. Increase the visibility here. So as you can see, we have already imported the dataset and we are using the Google Colab for this. You can perform the same on Jupyter Notebook if you like. It's up to you guys, whatever suits you better. So we are going to be performing EDA using Google Colab. So first of all, we have to load the dataset, and we have imported all these libraries. Pandas, because we are going to be using data frames here. NumPy for basic view computations. Matplotlib and Seaborn for visualization. So loading the data is very simple, guys. We can use the read.csv function over here from Pandas module and with the file name. If you're using Jupyter Notebook, you might have to give the directory over here, and you may find out that you're facing a few errors importing the data. But don't worry, guys, you can reach out to Intellipaat and we'll be happy to help you with this problem. And then with this, we are basically done loading the data. So the very first step that I'm doing over here is getting the name of the columns. So data.columns give me the column names. So we have city, country, name, year last expansion that we have discussed while discussing the description of all these columns in our data. Next up, we have data.info. So info is going to give me the information about, as you can see, we have three columns here. One is having the column name, basically all these names. Then we have the number of values and how many of them are non-null. So as you can see, we have 188, repeat. As you can see, we have 198 values over here, which are all non-null. The data type here is object for three columns. Then we have integer. The annual ridership is in float, and then we have object again. So we might have to change these data types if we are going to perform some linear regression, let's say. So that comes after we have gathered the insight or before we are preparing our data for the modeling. So that is also one of the things that we can cover in the EDA, where we look at all these data types and figure out which one needs to be converted to, let's say, integer. Now let's go ahead and check the shape of the data with data.shape. So we can see we have 198 by 9 is the shape of our data over here. We can check the dimensions also. So checking the dimensions helps you when you are performing, let's say you have a data which has 64 dimensions, then you may have to perform dimensionality reduction over there, which will help you in preparing your data for the modeling. And that is why checking the dimensions is also one of the good practices when you are doing EDA. Alright, so this is the part where we describe our data. So first of all, what we are doing is we are getting the first 5 rows in our data set using the data.head method over here. As you can see, the first 5 rows in our data, we have the cities, we have the country, the name of the metro, the year it was built, the last time it was expanded, and then we have the stations, the length in kilometers, annual ridership in million, and then Africa. So we have a lot of variables here which are not integer or float type. So what we are doing is we'll describe the data, but we are not going to get the values for those particular columns. Like if you can see over here, the describe method does not fetch us the count, mean, standard, minimum, 25 percentile, 50 percentile, 75 percentile, and maximum. For the columns, city, country, we don't have name over there. We won't be having region as well. So we have only got the year last expansion, the stations, length kilometer, and annual ridership. So this is one pointer that you can make a note of. Whenever you're using the describe method, it is not going to get you the values which is not in the type numbers, basically, which is integer, float, it could be a complex also. But if it is an object or a string data type, it is not going to get you these values. So describe is actually one of the methods which is quite useful while doing the EDA. So I can, for example, let's take this column, stations. So we can know what the count is, we know what the mean is, we know the standard deviation, we know the minimum, and there's a 25th percentile, that is a 50th percentile, then we get the 75th percentile as well, and the maximum also. So we know for sure the highest number of stations in the entire data is 424, the lowest is 6, and the mean value for all these metro stations is 68. Similarly, we can have the numbers on length kilometer. So the highest is 49,039 kilometers, and the lowest is basically 12 kilometers. So the metro station with the lowest network, or the lowest range of network, is 12 kilometers only. And then again, we have the minimum of annual ridership. So there is a station which does not even cross 1 million commuters every year, and the highest is 2834 million. So that is quite a number. So this simple 5-point summary you can get from describe method. So this is very crucial when you are doing the EDA for any data. You get the basic idea of how your data is. And then again, what we are doing is getting the unique values for region. So let's say we have this column region over here. So we can get all the unique values using the unique function over here, and we are printing those. So the number of unique values is 6, and the values are Africa, Latin America, Asia, Australia, Europe, and North America. Let's say if we wanted to narrow down our analysis only to one region, we can segregate the data based on this value and then perform our EDA on that particular set of data. So that is why we have done that, and we have done that same thing for countries. So we have 59 countries that has the metro network in our data, and these are the country names. And then again, if you do that for the cities, so 187 countries from the world in our data has the metro networks or metro trains. So this is a very simple finding from our data, which you can say in these 6 regions, 59 countries have metro stations, and out of these 59 countries, 187 cities are there. So that is our initial finding from the data. Now when we move on, let's check the distribution plots for each parameters. Now we are using Seaborn over here to create a distribution plot. Now distribution plot will tell you a lot about your data. Basically, it will give you if it's a normal distribution or if it is positively skewed or negatively skewed. So if you take a look at this data, this is negatively skewed because we have a lot of values towards the end of the distribution, and that is how we can estimate or basically interpret this data. So most of the metros were built after 1975, we can assume that, and the first ones were built somewhere around 1900s or before that, in very less numbers. When we take a look at the next plot, which is about the stations, this is also a skewed data, not a normal distribution. So most of the metro stations are in numbers 0 to 100, and only a very few metros have stations more than 200. So these are the findings we get from visualization. That is why data visualization is a very important aspect of performing EDA on any data. Now visualization can be it can be of any sort. You can find out the distribution, you can find out the relationship between the variables, you can find the outliers. So these are three basic things that we'll be covering in this session. But visualization is not just limited to finding out the distribution or the relationship. You can actually get beautiful insights or create dashboards using Plotly, or you can create a beautiful dashboards using Power BI and other tools available to you in the market. But we are only going to be using Matplotlib and Seaborn for this session. There's a surprise in the end where we'll be covering something interesting using Plotly. So hang on there if you are waiting to learn something new today. And moving on, there's another distribution plot where we are checking the distribution for the annual ridership. So there again we have a skewed data, and most of the ridership or the annual ridership falls between 0 to 500 million, and only a few goes until let's say crosses 2500 million annual riders. And then we go on to check the distribution of last year expansion. This is also skewed, and we can clearly see that most of the expansions happened after 2000. So that is how you easily find out the distributions here and make quick assumptions about the data using these values. So from these few plots, I know that most of the stations or the most of the metros that are located in these cities, countries, has less than 200 stations, were built after 1975, and the annual ridership is less than 500 million, and were probably expanded after 2000. So these are the insights I have gathered so far. Moving further, I check the distribution for the length of kilometers, and this is where it gets interesting. So mostly all of the data falls under 10,000 kilometers. So that is where our distribution is not very helpful. So we'll be taking a look at this particular parameter while checking the box plot, so that we can get a clear idea about how the data is distributed. Now we do the outlier analysis with box plots. Now box plots is not just about finding out the outliers, which is basically whatever values we're getting outside this particular line over here. These are the outliers, but we can get the median values, we can get the percentiles over here, which is the IQR range, minimum and max, and these are the whiskers. So these are the values, and we can clearly see that year is negatively skewed. So we hardly get any, what do you call it? So we can hardly get any normal distributions in this particular data that we are handling right now. So there's no normal distribution. So let's say if we are going to use this for linear regression, we might have to scale the data so that the standard deviation and mean is actually normalized, and that you can check out in other sessions where we have covered linear regression, guys. Now coming back to our session, we have gathered some insight on the outliers for the year column. Now what we'll do is we are basically going to get all the values before 1925, because that's where our outliers lie, before 1925. So we are taking a rough number here, and then this is the data for all those metro stations which falls under this range, the outliers basically. And we have created a few plots over here, the visualization plots, to understand this data, the outliers. So we have a bar plot over here where X is the number of stations and Y is the city. The hue we have taken as region. So if you take a look at this, blue is represented by Latin America, orange is in Europe, and North America is denoted by green. So by looking at this plot, I can clearly say that most of the metro stations that were built before 1925 were built in Europe. So that is how I can make an assumption or an interpretation from this plot. And only a few were built in Latin America, and the other ones, the other majority falls into North America. And this also shows that New York has, let's say, New York has been mentioned twice over here. So that is why we get the line over here in this bar plot, multiple values. Now let's move on to the next one. Next bar plot is the length of kilometer and the city. Now I can make assumption about these because most of the metros that were built in Europe has a length of kilometer which is higher than everybody else, which falls under London. So my assumption from this plot is the metro station built in London or the subway built in London has the length in highest numbers that were built before 1925. So like this you can make assumptions about the data. So these are the findings that we are gathering through this EDA. Similarly, we have another plot where we are checking the annual ridership. Then again, I can make an assumption over here that Paris or the subway or metro station that was built in Paris has the annual ridership in millions in highest numbers which was built before 1925. So that is how you gather all the insights on the data, and this is basically what we are doing with the outliers. We're just checking the values of the outliers over here, and then again we can also create the histograms over here where we have added the hue as region again, and there we have done the same thing. You can figure out the number of stations fall under the Europe region that are in the highest numbers, and surprisingly North America has more than 400 stations. That is basically the highest over here. Annual ridership, if we check for this, that is 639 million. Alright, so I actually want to correct myself. It is not Paris which has the most number of stations. It is New York City, guys. One second, let me just correct myself. Yes, it is New York City that has the most number of stations. Alright, so let's move on. And similarly, we have done that for length of kilometers and annual ridership again. And same thing we have done for every column. We have checked the outliers for year last expansion, and most of them fall before 2005. So we have taken the number as 2000 over here. Anything built before 2000 we have over here. And we do the same thing. We check the annual ridership. We check the number of stations. We check the length of kilometer, and then we provide some histograms to get the better idea of how the number of stations looks like. There we have Asia again in this, and so we can also make a conclusion that most of the metro stations that were built in Asia started after 1925. So that is one assumption. We can get a clear number on that when we check the very first metro that was built in Asia. And this is how we can gather a few insights on the outliers. Now moving on, we have done the same for length in kilometers also. So anything after 2000, let's say, or 2300 we have taken over here, is falling outside the range, which is the outliers, and we have all these metro stations. Most of these falls under China, guys.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
And we have done the same thing. We have created the histograms for annual ridership. So annual ridership falls majorly in 0 to 500 million, and then we have the number of stations, which also falls majorly in 0 to 50, let's say 0 to 70 stations. And the histogram shows for length in kilometers according to region. So we have most for Asia because most of the stations are in China. That is why it all looks blue, guys. And if you take a look at Europe over here, we only have two cities, Madrid and London, which shows the length in kilometer. And this basically is where we can conclude that so the largest network of trains exist in Asia. So this is the conclusion from our analysis over here. And then again, we can check the annual ridership and all these things. So we have done the same thing for stations also. We have taken all the stations more than 200 are going to be in the outlier section. So we have all these cities over here. We have done the same thing again, plotted a few bar plots to get the clear idea on length on kilometers. So I think Delhi tops the chart over here, and then we have the number of stations. I'm sorry guys, this is the length in kilometers that we're talking about for Delhi. So that is the highest for any city that has more than 200 stations. And if we check that for number of stations, the most comes with Beijing and Shanghai. There is Paris from Europe, Madrid, London, and New York City. So I think New York City is the highest. Then on the second place we might be having Shanghai. And then we have Beijing also. Then we check for annual ridership. The hue is region over here again. So we have Asia, Europe, and North America. Surprisingly, we do not have Latin America in this. So probably Latin America does not have the metro network which has more than 200 stations. So that we can conclude. And similarly, we have created a few histograms over here, and it is dominated by the Asian region for annual ridership, for stations, for length in kilometers. Number of stations actually is shared by North America, where New York City tops the chart. And then again we have a box plot for annual ridership, where everything after 500 million is an outlier. So we have segregated the data based on this, which is greater than 600 million. That's going to be in our outliers list. So that is how we can analyze this data, check the annual ridership, which is highest in Shanghai. Similarly, Tokyo also has a few concerns over here, and then we have Beijing, then we have Delhi also, Moscow, Mexico City from Latin America is also there, and then North America we have New York City. So majorly all the regions are here. Only the Australian region is not present over here, but let's carry on. And then when we check for stations, then again Beijing, Shanghai, Seoul, and then we have Mexico City from the Latin American region, and New York City, of course, it's topping the chart again here, which we already have concluded. When we check for length in kilometers, first of all we have Delhi, then there is Xi'an, Moscow, Mexico City again, and Sao Paulo is also there from Brazil. And alright, so when we check the histograms, there we can see the Asian region dominating the charts over here. So this is why we have used the visualizations to get beautiful insights from the data, which we might not be able to get just by looking at the data or just by inspecting it. Like if I just take a look at the 5 rows or the entire rows of the data over here, I might not be able to fix or gather a few insights related to this data, but through visualization I was able to do that. Now moving further, let's talk about how we fix the outliers. So I'll quickly give you a preview of what we have to do for that. So handling outliers is not a very big task. Like most of the times we can leave the outliers in the data because they might help in reaching a conclusion, because they are very useful information, the outliers also. Like for our metro data again, we might not want to do this because the information that we get from outliers is extreme but is important because those are facts. So this is just an example of how you can get your data fixed or remove the outliers. You get the IQR range, which is the 75th percentile minus the 25th percentile, and these are all the IQR range for every column. For year it is 36.75, for year last expansion is 7, stations is 69.75, length kilometers, and annual ridership. So what you can do is basically replace the values with this particular thing where anything above or beyond the range, the IQR range, we are going to replace it with that. So we are going to skip this part because we want to keep the outliers so that we understand the data better. And let's also check the number of null values. Since we do not have any null values in this particular data, what I'm going to tell you is how you can replace them. The first option is always to drop the null values. Then again, you can fill the null values with 0 or with mean or with median if you don't want bias in your columns, because if the distribution is not normal, you can replace the column values or the null values with the median. And then again, if it's object data type, you can replace the values with the mode, and that is how you can treat your data for data imputation, basically replacing the null values. Moving further, to understand the relationship between the columns, what you can do is basically plot a few scatter plots and you will get the idea of how your relationship in between the columns is. So let's say if I wanted to quickly summarize or use this entire data to decide the annual ridership. What I'll do is check the relationship with all these values or all these columns with annual ridership, so that I get a clear idea if length in kilometer is going to affect the annual ridership, if stations, number of stations is going to affect this, if the region is affecting this particular value, or if the last expansion that happened has affected the annual ridership. That I can find out by using the scatter plots. So scatter plot between the stations and length kilometers is showing a considerable amount of increase, but not that great. So we can't really say it has a linear relationship. But for stations and annual ridership, it clearly shows a linear relationship, not exactly that strong, but it just shows that there is a relationship between these two variables. Then again, if we check for length in kilometers and annual ridership, it's not exactly that strong, but we can say it's gradually increasing. So there is a clear sign of increase, but not that strong. When we check for year and year last expansion, it's not really great. We have taken the limit from 2000 to 2022 because most of the expansions happened in that time. Similarly, for X limit also we have taken that for length in kilometers. And when we check for year and stations, this also does not show a considerable amount of relationship. So this does not actually show a very good relationship between the two. For year and length kilometers also, there we can't find any considerable amount of relationship. And then again, if we plot all these subplots, these are the subplots that you can get: annual ridership with respect to built year, annual ridership with respect to stations, annual ridership with respect to expansion, and length. So length shows somewhat linear relationship, and the number of stations also show. So these two variables or these two features in the data are going to be very useful for us if we go for a linear regression model, let's say. So these two will be able to decide how our data looks like and how we can actually predict some of these values. Since we have not used any of the object columns, if we do a little bit of hot encoding or label encoding on that, we might be able to find out relationship in the over there as well. So you can take that up as an exercise. So I'll tell you two questions you can solve. Convert the object data type in this particular data into an integer data type, or perform label encoding in that, and find out the relationship between those variables and the annual ridership column. So that is one exercise you can take from this session. And then again, if you just want to get the relationship easily, you can just use the pair plot, which gives you all these plots with respect to each of the columns. And with the annual ridership in millions, we can see two columns that are showing considerable amount of linear relationship. And we are going to conclude with that. We can add the hue as a region also, where blue is Africa, then we have orange, which is Australia, Europe is in green, Latin America in red, North America and Asia. So if we check over there, the extremes are on the Europe over here, number of stations, and length in kilometer is in North America, the extreme. That is how we can visualize the data, guys, to gather insights. We can also create a regression plot. So annual ridership and the two columns that we have gathered, which is station. So the best fit line is over there, and here the error we can reduce. And same again, if we plot this for annual ridership in million with length in kilometers. So that is how we plot the regression line also. Now to sum up this session, let's also do a little bit of region wise analysis, and also a little surprise for you, where we have used a few pie plots using Plotly. So that is something that looks interesting and gives you a better picture of the entire data. Alright, so we get the unique values, which is all these 6 regions. We segregate the data based on all these regions. We're using the data.loc or loc, where the region is equal to Africa, Latin America, Asia, Australia, Europe and North America. Now what we're doing is we're using Plotly for sunburst, which looks like a pie plot, but it actually opens up when you click on these. Alright, so just to quickly give you a review on this, we'll go to the Asian and let's check for Latin America first. So this is sunburst, which is going to give us the clear picture of the entire data or the entire metro network in the Latin America. What we have is all these countries. So these are countries, let's say. Alright, I'm sorry guys, these are not the countries. So we've only used the region, the city name and stations. We have not used the countries. I'm sorry guys, these are not the countries. So if I click on Caracas, we have the Caracas Metro, and which has 52 stations, and the annual ridership in million is 358. Let's go back. Let's check for Medellin, and we have the Medellin Metro, which has 27 stations, and the ridership in million is 115. So I can check that for every city that we have in Latin America or in Africa. For in Africa, we have only one city, which is Algiers Metro, which has 19 stations and 45.3 million annual ridership. So this quickly summarized all the data based on regions. So that is how I have segregated the data. If we take a look at Rio de Janeiro, we have the Rio de Janeiro Metro, which has 41 stations, and the annual ridership is 118.7. Now when we have a lot of cities, we have a lot of these columns. So what we can do is we just check for the number of stations over here. Let's say we go to Seoul. Seoul has two metros. We have the Korail metro lines, which has 86 stations and 426.4 ridership in millions. And then we have the Shimbodang line New Trans, which has 12 stations and 122.5 ridership in millions. Then in Asia, we can check for other cities. Okay, let's go to Istanbul. So we have the Istanbul Metro, 107 stations. There might be there's Manila over there, which has the Manila Light Train System. Repeat, the Manila Light Rail Transit System, and number of stations is 33 and 218.2 million ridership. Alright guys, so that is all about how we can create a sunburst. So in Bangkok we have BTS SkyTrain, the Metropolitan Rapid Transit, 53 and 60 stations, annual ridership 236.9 and 95.3. So we have Bengaluru also, which is Nama Metro with 51 stations and 174.22 million riders or commuters every year. We have Hyderabad Metro also, which has 56 stations, and these are all the summary of all the cities that has metro in the Asian region. St. Petersburg is also there, the St. Petersburg's Metro, 64 stations and 495 million. So that basically gives me a summary. Then we have for Australia with Sydney Metro, has 13 stations and 12.9 million users. And then we have for Europe, Milan, Munich, Vienna, all these values, the Lisbon, Warsaw, Minsk, and we have Prague, Kiev, Rome. So for Kiev we have the Kiev Metro, which has 52 stations and 279.5 million riders every year. We have for Lisbon, the Lisbon Metro, 56 stations and 184.6 million riders every year. And Barcelona we have for Vienna actually has Vienna U-Bahn, 98 stations with 459.8 million annual ridership. So if we take a look at this Warsaw Metro we have, and similarly we've done that for the North America also. So we have Montreal, Toronto, Vancouver, Washington DC, and there's Miami also. So a sunburst is something that you can use to get a clear picture of all the data points in your data set. Now last but not the least, I want to talk about the data correlation, which gives you a better picture of all the variables that are going to be correlated to each other. And if we check for annual ridership in million, we can see stations and length in kilometers is showing a positive correlation, where stations is actually showing a strong positive correlation, whereas length in kilometers is not that strong but is considerably showing somewhat correlated values over here for annual ridership. So this is where we are going to sum up our session, guys. If you have any questions, you can mention them in the comment section below. And now that we have come to the end of the session, don't forget to subscribe to Intellipaat for more exciting videos, and press the bell icon to get the latest updates from Intellipaat. Also, tell us in the comments about your journey as an aspiring data scientist, which areas excite you the most, and where we can help you master data science concepts in the best possible ways. Thank you.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.